That last topic of the unit 2 has to do with motion that involves both translational and rotation motion. Okay, so we had talked about this before as well, that we can decompose this complicated motion of an object that is doing translation and rotational motion together into individual motions. Okay, and we can assume that the object is just rotating, for instance, and then we can just assume that the object is just doing translation, and then we can add both of these together to get the complete motion when an object is doing translation as well as rotation. And we can study problems where such kind of motion is happening, which is very common. If you just see a car that is moving, you will see that the tires are doing this kind of motion, right? So a very familiar motion. If you see a ball that is rolling on the surface of a table or the road, then even the ball is doing that kind of motion. Okay, so again, what you have to remember is that this rolling motion, okay, will not be possible without friction. Okay, so if there is no friction and the object is rotating, it will just keep rotating about where it is situated. Okay, and if something is just sliding, and then it will just keep sliding, and it won't actually start rotating until unless there is some friction acting on it. Okay, so that's the picture here. Okay, so you have to remember that the friction plays an integral part in these situations. Okay, so again, what we have to remember is that we can look at this motion of the object that is doing this translation and the rotation in terms of the motion of the center of mass. Okay, so uh, when the object is actually not slipping, we have the relationship that V is equal to R omega. Okay, so let's see how the motion can be decomposed. Okay, so we have again the entire system, and we want to find the kinetic energy of the system. Okay, and we already know from before that if there is no external force acting on the system, then the total momentum of the particles will remain constant. Okay, that's our conservation of momentum. However, we know that the mechanical energy can change, okay, from one position to the other, so there is no restriction on that. All right, so let's look at the kinetic energy of this total system. And again, we are going to consider just a small mass element somewhere here, mi, and we know that we can just write half of mass times velocity of that element square. Okay, so now what we are going to do is we are going to transform this to our value in terms of the center of mass. So the velocity of this object will be just the velocity of center of mass times the position of the object with respect to the center of mass. Okay, so we are going to decompose that vectors and put it into those equation here. Okay, and if we do that, we get the expression as 1/2 mi times v of the center of mass square plus 2 times v to the center of mass times this position with respect to the center of mass plus u of I square. Okay, and this term, that is u of I m of I, this is the total momentum with respect to the center of mass. So that's just saying that if you are situated at the center of mass and the object is moving with a constant speed, you will not feel anything, you will not be able to know whether the object is actually moving, right? And this is very similar to our situation on Earth, right? We know that the Earth is moving with certain velocity, okay, but we can rarely feel it because we are on the Earth, right? But if you are on a different frame of reference and you are seeing the Earth move, right, with respect to your frame of reference, maybe you are on moon, then you will be able to see the Earth move, right? So when you are at the center of mass, you will not be able to feel the motion, right? So that it feels like your momentum will be zero with respect to that. Okay, so this expression for the kinetic energy reduces down to this expression that kinetic energy total is just 1/2 mi times velocity of center of mass square plus 1/2 mi ui square. Okay, and here the velocity of center of mass is constant, so it can come out. You're just integrating over the entire mass, so you get the total mass. 1 half m total mass times center of velocity of center of mass square. And the other expression, again, you're calculating for u of I, and again we can write in terms of omega and r like we were doing before in many cases, and then you get that this expression becomes 1 half I of center of mass times omega square. Okay, and simply stating that total kinetic energy of the rotation can be decomposed into the rotational kinetic energy about the center of mass plus the translational kinetic energy of the center of mass. Okay. So let's look at this example and try to understand what is going on in this system. We have a bicycle that is going with some initial velocity, that's 8.4 meters per second, and it comes to rest after 115 meters. Okay, so there has to be some deceleration. Okay, and we have been given that the diameter of the wheel of this bicycle is 0.68 meters. Okay, so the radius is 0.34 meters. Okay, so we want to find the values of omega, the alpha, the acceleration, and the time when this bike will come to a stop. Okay, and if it does that, then it can avoid hitting this fire hydrant. Okay, so again, to get the value of omega, all you have to do is you have to use the relationship v is omega times r. Remember, there is no slipping in this motion, so it is a smooth motion, it's just doing rotation. There is no sliding or no slipping in this motion. Okay, so you can use this relationship, and again with the same idea you can calculate the displacement that is happening, that is the total angular rotations divided by the radius, and so you get the total number of revolutions that it is doing. And from here you can just use your equation to calculate the value for acceleration, which will just be omega square minus omega 0 square divided by 2 theta. Okay, and if you do that, you will get the value for alpha, which is the deceleration that this object has to go. Okay, and to get the time now, you can use the another equation. Remember, omega 0 is omega plus alpha t, and if you do that, you can get the time that this object will travel before it stops. Okay, and later I would like you to try to solve this and confirm these values. Okay, so that's a simple application of what you have here as an object that is doing rotation as well as translation, and we can use some kinematics equation and this important relationship of v is equal to omega r to solve a problem like this. Okay, so what I want you to do is I want you to look at a much more difficult problem than this. Okay, so we have a bowling ball. If any of you have ever gone bowling, it will be much easier for you to understand this. So you have a bowling ball of some mass m and it has some radius r. Okay, so it's a completely solid sphere. Okay, and the person throws the ball, and as soon as it hits the floor, the ball basically starts slipping or it starts sliding so that it doesn't rotate. Okay, so let me make it more clear. The point here is a on top, and so it is not slipping, so the point a stays as point a and just slides over a distance s. Okay, and it does that why? Because there is some friction on the floor. The value for the coefficient of friction is given as 0.2. Okay, now when you throw the ball and it hits the floor, the initial velocity is given as 3 meters per second. Okay, and you have the value of the friction also 0.2. Now what you have to do is you have to find the time that the ball will slide before it starts rotating. Okay, and you have to also find the distance that the ball slides before it starts rotating. So here until this point it is completely slipping, and beyond this point, okay, it starts rotating. Okay, I'll give you a hint that you have to decompose the forces to actually calculate the values for your time and the distance. Okay, so in this problem that we have, when the ball strikes this floor, okay, because of the friction it starts sliding, so there is no rotation that is happening from this position x1 to x2. Okay, so in this situation from x1 to x2, we have to use the equations of kinematics that we know. Okay, and we already know that we have to consider the motion of this object with respect to the center of mass. Okay, and what is the problem asking? The problem is asking us to tell us the distance that the ball slides before it rolls without slipping. Okay, so we want to find this value of s. Okay, so we know to calculate the distance, we need v0t plus 1 half a t square. This is the expression that we need. Okay, so again v0, this term for us is given. Okay, so initial velocity is given. Okay, so we need the time and we need the value for your acceleration of center of mass. These are the two terms that we need. Okay, so the first part of the problem is telling us to find the time anyways. Okay, so what we need is a of center of mass and time. So let's calculate these two quantities. Okay, and remember here when we are going from x1 to x2, it is not doing any rotation, so this omega 0, the initial rotation of the object, is 0. Okay, and that is the situation when it reaches here and then it starts rolling. Okay, so when it starts rolling, we know that at that situation v is equal to r times omega. That is only valid after the position x2 and at x2. That's the validity condition. Okay, so let's start by again decomposing the forces. We know that there is the normal force acting here because it's in contact with the surface, and you have the gravitational force mg acting in the opposite direction, and you have the force of friction that is opposing the direction of motion. So these are the three forces that are at play in this situation. Okay, and it is moving with some initial velocity v0. So the first thing that we have to do is we have to write the equations of motion in the x and the y direction. Okay, so summation of forces in the x direction, right, will be mass time acceleration in the x direction. That is your equation of motion for Newton's second law. So what are the forces in the x direction? So if this is your x direction, we have to define this as the x direction, we have to define this as the y direction. That's our convention. We have to use this as the positive sign. So that implies your force in the x direction, you have only one force, which is this force of friction, and that also is in the opposite direction. So minus force of friction is equal to your mass of this object times your acceleration of this object. Okay, so there you go. That is your acceleration of this object. Okay, in the x direction. So what is the force of friction? To calculate the force of friction, we know that if we sum the forces in the y direction, because the object is not moving in that y direction, that should be 0. That means your value of n minus mg has to be equal to 0, or n is equal to m times g. Okay, so now the force of friction is given by the kinetic energy terms times the normal value. Okay, so my value will be mu mg. Okay, so when I plug it into this equation here, 1, I will get that m a of x is equal to minus of uk m g. Okay, and my m and n will cancel. So I'm getting my value of acceleration is equal to minus of mu k times g. Okay, so I've already found one expression right here. Okay, so in this term I need acceleration. I already have that. The acceleration along the x-axis is what I need, and that is what I have here because the object is moving in the x direction. Okay, so that is the value. So now I need to find the time. Okay, so to find the time, what we can do is we can use the relationship of v of center of mass as v0 plus the acceleration center of mass times time. Okay, now here this expression will become v0 minus mu of k times g times t. Okay, so that is the expression that you get for v of center of mass. Okay, Well, it's fine, whatever. Let's consider that as the value of V of center of mass. So now at the situation, at this point here, we know that V of center of mass at x2 is equal to R times omega. That is a relationship. Okay. So that means I can plug in the value of omega and equate it to this equation right here. So let me call this equation 2, let me call this equation 3, and let me call this equation 4. Okay, and let me write that down here so that there is no confusion at x2. Okay, so I need to find omega. So how do I find omega? Omega is omega 0 plus alpha t. Okay, now omega 0 is 0. So I know that this value is 0. That will just be alpha t. So I need to calculate alpha. How do I calculate alpha? I need torque. So torque is I times alpha. Okay, so what are the forces that are acting in the system? There is only frictional force acting in the system. Okay, that is creating this torque. Okay, so torque we know is R cross F, right? I is 2 by 5 mmr square. So this we know 2 by 5 mmr square. Okay, times alpha is the right hand side, and what is the left hand side? It will be R cross F. So you have R, and what is the value of force? Force is UK times mg. So UK यहाँ हमने निकाला था times m times g. Okay, so that is the value. So if we look at this equation, यहाँ पे क्या होगा? R R कट जाएगा, एक R बच जाएगा, है ना? मास कट जाएगा. So यहाँ से हमको अल्फा की रिलेशनशिप मिल रही है. अल्फा इज इक्वल टू 5 दूसरी तरफ चले जाएगा, तो यू गेट 5 हाफ u of k यहाँ पे है. Okay, and what else is left? G is left and one R is left here. Is equal to omega 0 plus alpha t. We can substitute it here. Okay, so once we have alpha, then I can say my omega will be 5 half u of k g t by R. Okay, R times 5 half mu of k g t by R is omega. Okay, is equal to v0 minus right hand side में क्या है? u of k g t. Okay, so I'm seeing that my R and R is cancelling. I have uk jt and uk jt. So this is exactly the same term. So I get v0 is equal to 5 halves plus 1. I'll take this on the other side times u of k times g times t. Okay, so that means I'm getting the initial velocity as 7 half u of k times g times t. Okay, so there you go. I have an expression of time relating to the initial velocity. Okay, so let's calculate this. Because I know uk, I know j, that's 9.8. I know initial velocity, so now I can calculate time. So, and I'm getting the value as great 0.43, and that is seconds. Wait, this is v0, this is t. Good. So t aa gaya. So again in our relationship, where is our expression that we need? The final one, which is right here. Right, v0 aa gaya, t bhi aa gaya, a bhi aa gaya. So अब delta x calculate करो, क्या आ रही value? Because a of center of mass is the negative term minus u of k times g है. Saloni is getting 1.124. Even I am getting 1.124.